In this segment, we're going to start to take a look at our roof framing. And our resident expert, Professor Zimfer, I think will get us started and go through what the nomenclature is, what we call everything, and then we'll go into the whys.
Absolutely. Thanks, Scott. As you can see here, we've shortened our structure down. So this is a good teaching tool so we can work effectively kind of at roof height, but by bringing our wall height down, we can be safe and not be on scaffolding and ladders. So if you're wondering why we're so close to the ground, it's for safety reasons. So this short wall here represents our top plate, top of wall. So this could be on a ranch level or single story. It could be 2 or 3 stories into the air. So you still see we have the same components, a bottom plate, a common stud, and a double top plate. So from there, it would be time to do a roof layout or a framing layout for our roofing members. So in this case, we have a stick framed or stick built roof. So we're using rafters, and we're using a ridge beam up at the top. Now, the most common method used right now in wood construction would be an engineered truss. And that's an off-site component. It's built by a truss manufacturing plant. It's designed structurally by usually their in-house engineering staff to work out pitches and bracing and everything that would need to be done. They're built at the plant and delivered to the job site and then lifted into place using a crane in most cases. Sometimes they can be lifted by hand if they're small enough. And the trusses can be enormous. They can be upwards of 20 feet tall, they can be 40 plus feet long, all kinds of different ceiling configurations on the inside. They can control their overhangs or their soffit or eaves. So there's a lot that can be done with the truss. Because we don't have room, we start with stick framing the roof, but it also teaches a few more skills or steps that are needed. So let's go through some of the nomenclature first, and then we'll talk about technique next. So as I said, this is a rafter. Here we've made them out of 2x8s. In most cases, unless it's a really short run, it's going to be at least a 2x8. 2x10s, 2x12s, and then we can also use things like the engineered I-joists that we talked about in the flooring sequence. We can use those engineered I-joists, 14 inches, 16 inches, 11 and 7/8, and we can run those as rafters as well. Again, with all these things, we want to make sure that we're using the right product in the right location, and if we're worried about any loads, say a snow load that would be on a roof in a certain part of the country, that we're doing it within the accepted norms. We don't want to have any roof failures because that would be catastrophic. And in general, the roof has one purpose. It's to keep the elements out. When we get into the details, there's architectural reasons why we do things. We want things to look pretty, but the roof basically has one purpose, and that's to keep that element out and keep our occupants, warm or cool, dry, and safe. At the top of the structure, we have a ridge beam, and that's going to run through. We can break that ridge beam periodically, and we'll have to worry about the splice and how we connect it. So these start to get pretty intricate on how we cut. We need to match our pitch angle up here, and by pitch of the roof, I mean our rise here, vertical rise versus the run. So we could have a 312, meaning every foot that we go this way, we would rise this way 3 inches, or a 412, a 612, say a 912, a 1212, which is starting to get pretty steep, right, Scott?
Yep, absolutely.
Once we get above a 912, I think it's considered a non-walker, or 912 and up. You can't walk that roof anymore without some extra precautions put in place.
Absolutely. So Mark, why do we have some framing on the end of the gable end of the structure of the roofing system? We see some vertical elements there, some almost like they're studs.
Right.
So what is that framing for?
Yeah. So here we have framed what would be a gable. Another common roof type is a hip, and that's, instead of this, the roof would be kind of laid back in, just like it is here.
Right.
Well, here, architecturally, maybe the design said that we wanted to have our siding or our brick coming all the way up to the peak. So we needed a gable. Well, when we do that, we have to have some bracing here. It's really not for the roof structure, but it's just like we did our walls. We need to have a layout that we can attach our structural sheathing to, our foam board, our siding to. So in this case, they just followed a very simple 2-foot on center pattern. So if you picture that structural OSB coming in here, it gives a place that we can attach that sheeting to, and then our finished product come all the way up and cover.
All right.
If this was a hip, this would be laid back in per the plan, and the hip roof would then have shingles on it, and our finished product line would stop right at the bottom of the hip, the same way it would on our big gutter runs across the roof.
Okay. So why don't we take a look at what we've got on the outside? So when we bring the fly of the rafter past the outside of the wall, we get this overhang. And what this overhang creates is, we'll take a look at some of these parts a little bit later, but creates a fascia and a soffit area.
To help create the fascia and soffit area, we have a plunge cut, so we can get back to where we're perfectly square or perpendicular to the structure. We also have what's called a bird's mouth cut right here, so that way our framing member can sit tight to the top plate. We need to make good contact. If we didn't cut this 90 bird's mouth here, then think about our connection point. Our member would be sliding down the roof and only make very light contact. And we need to make sure that we've got good bearing right there and a good attachment point where we can attach that rafter, because this all works as a system. If we remove one of these pieces, the system gets weak.
So by creating this here, how do we do that on the end of the structure? We've got some framing up here. Could you please explain what this ladder system, kind of looks like a ladder to me.
Yeah, it does, and that's exactly one of the terms that would be used. A ladder, a chicken ladder, because it looks like the old ladders they used to make going up to a chicken coop. So we would just build this assembly. It can be done several different ways. If we only have a short soffit, in this case, our soffit was set up to be a 12-inch overhang, which is a pretty common soffit or eave. We can build that down on the ground, and then we can lift the whole assembly up and attach it. This would be done before our roof decking or roof sheathing would go on. Another way to do it is if we're going with deeper overhangs, 18 inches, 2 foot, 3 foot, again, referring back to the plans and specs, we would actually cut in blocking into our rafters and run that block back 2 or 3 rafters and create a lookout. And off of that lookout, we could then hang our ladder system. It just, the farther we go out, the more bracing we need. Right. So that creates that seamless look all the way around. Now, this piece is not necessary. Some plans and specs down on the gutter runs will show an overhang, and then on the gable ends, they'll just put a little piece of trim that sticks out 1 inch. Our finished material butts in right into that piece of trim, and then the shingles overhang the trim by another 1/2 inch to 1 inch. So this, again, is going to be specific to whichever plans and specs that you're working from.
Very good. Very good. So what do you think are some of the pros and cons of stick building a roof opposed to using a truss system?
Sure. So in stick built, it allows us to fill in some really difficult areas. You think of a truss system. There's only so many configurations they can make that truss. So when we frame in with trusses, a lot of times we'll get a strange valley that comes together with 2 trusses, and it'll leave a part of the roof that needs to be stick built. Maybe it's a custom pitch that has to be done right there. Maybe it's something very special like a turret where we're turning a radius with the roof, or doing an eyebrow, which is an arch that comes up out of the roof like an eyebrow over the top of an arched window. In those cases, we're going to have to stick built because those are very special items. It's the trusses are no more than just a manufacturing product. And when you think about manufacturing, they're very good, fast, efficient at cranking out common parts and pieces. So when you get outside of the common parts and pieces, that's when we have to do a little more stick framing.
So one thing that I always saw, because I was trained to cut in a roof when I was carpentering,
Sure,
way back when. As a matter of fact, I didn't even know what a truss was first time I nailed up, we cut a roof in. The one thing I did see was, with the instability of lumber today, a stick-built roof sometimes can get some, it looks like the ocean, just the waves going down the roof because of the quality of the lumber we're sent to the site a lot of times.
Right.
So there's a lot more work that goes into this type of roof, and not always for a better quality product.
Absolutely. Right? And it really comes down to the part, like when we're talking the United States, the part of the country you're in. Texas is famous for still doing a lot of stick-built roofs. And Texas is a big market for production home builders, so you would think that trusses would be right up their alley because they're building the same models over and over again, but it's just the workforce there doesn't have the training with trusses. So we get into a stick-built roof, and that's what they like. But you're right. We talked about in our framing sequence about scouting our lumber, holding the lumber up and looking down the edges and making sure there weren't any bows and twists. Well, now think about these great big pieces. These could be 24, 26, 28 foot long, and we're looking for those same things. So it's hard to find a piece of lumber that's 11 1/4 inches tall, 28 feet long, and doesn't have some type of bow or twist. Right. And then we get into air, right? User air. It happens all the time in construction. Our buildings are only as good as our installers. So when we look at what's been done here, we can see some similarities to our wall construction, right? We had to do a layout. We had to do a layout on the top plate. We had to do a layout on our ridge beam. And so we can land on our layout because we still want to break those sheet goods. Typically, we're still working with that 4x8 sheet good, and we'd like to break the sheet good in the middle of our framing member. So in our wall sequence, we did 16-inch on center. In trusses and rafters, again, based on the spec, we have to look, but in most cases, we're going to be 2 foot on center. And that's what they've done here, is lay a 2 foot on center so we can hit our layout, but then that lets us break that sheet right in the middle. So we have one sheet that would head that way, another sheet that would head this way. So once we hit our layout, we can start installing, but then we get into user air. So if we can show down the roof, we'll show a great sequence of user air. Because if we don't lift these rafters and hit our point exactly where we need to be up here, if we're higher than our ridge beam, we've created a hill in our sheet goods. If we would lower the top of our rafter from our ridge beam, even 3/16 of an inch, that creates a valley in our sheet goods or our roof decking. And you can see that right through here. When we look down the roof, we look at how level the sheet is, and we can see there's a low spot right here. And if we look up at the top of our rafter, we can see that we didn't hit the top of our ridge. As we come further down, we can see in this rafter that we were above our ridge, and that's now created a hump. So we've exaggerated the mistake because we went low here and high here, and now we've got this big change in the slope. Structurally, is it okay? Yes, it's still okay, but visually, it's not good, right? People are paying for a building, and they had a picture on the blueprint of what it's supposed to look like. And these valleys and hills will probably shorten the lifespan of the roof structure in general, the shingles and things like that, because they're not planing out the way they should be.
So what are some of these members that we have in here? We've got these pieces of lumber that are nailed across parallel with the run of the rafter, kind of attaching them.
Yeah, right. So these are collars or collar ties. And this is part of the assembly. You can see here we've used all of our scrap lumber up in the lab. We were using a 2x8, a 2x4, a 2x6. We were just doing this to make sure the roof was structurally sound and to talk a little bit about the mechanics. So when we think about how this rafter and ridge beam is working, they're leaning against each other and they're applying a lot of pressure against each other, but that also makes the bottom, if you picture my elbows as the bottom of the rafter, you put pressure here, it makes it want to spread at the bottom. Now, depending on the wall height and how many interior walls we have that are tying that building together, these walls are wanting to fold out as well with the pressure coming down the rafter. So what the collar tie does is create a force coming across that helps prevent that spread at the bottom. So in a truss that would come from the engineering plant, not only would we see the collar tie there, usually in the truss, it actually builds your ceiling. So we would see what they call the bottom chord. This would be considered the top chord. And then there'd be another framing member that would go right across here, all the way across the room, if my room's down here, and that would help be the bottom chord, or is the bottom chord. That also helps prevent the spread, but it creates the ceiling that would attach my drywall to. And now we've boxed out the room. In this case, we could still drywall this. This would be some kind of vaulted ceiling where we want some volume above our heads, whether that's a cathedral ceiling or it could be a tray or a boxed in ceiling, and we'll show some examples of that as well. But we said earlier that it's a system. So if you remove one of these pieces, if we're weak at a ridge beam, or we missed a collar tie, or we didn't have some proper bracing put in, the whole system gets weak. So when we buy those engineered products, we've said that it's imperative to follow the instructions. When that truss package comes out to the job, there's a big packet that comes with it. It shows the individual diagrams of each truss. It shows the layout, usually as a lettered system. It starts with A, and then it may go A 1, 2, 3, 4, 5, 6, 7, depending on how many trusses there are that are the A type. Then it'll switch to B. And there's been projects that are big enough where they start the alphabet over. They go to AA, BB, and keep going depending on how large the project is. But what's critical is not only putting those trusses in their correct spot and getting them perfectly plumb. We can't have that truss lean over one way or the other because that'll make it a little weaker. There's also stamping done on the trusses. And there'll be a stamp, depending on the manufacturer, in some kind of ink that'll say like brace required. Or sometimes it'll just be a mark like an X. And that's telling the installers they need to supply, after the fact in the field, another piece of bracing that runs through the roof system to help tie all those components together. And if we miss a brace, the roof is weak. So that's part of your QA, QC, our quality assurance, quality control, looking, did we put in all the bracing and all the blocking that was necessary?
That's an important point. In anything we do, we're always going to those shop drawings and making sure that our installation matches what the manufacturer suggested. That's a minimum standard, right?
Right.
We can always go up and beyond and make things even stronger, but they have a minimum for what this system was designed
Absolutely.
to hold up in the air.
Yeah.
Because I'll tell you, in Indiana, and the further north you go, what do we face every year for 4 or 5 months of the year? A snow load,
Right.
ice. You know, when you take water at, 8 pounds plus or minus per gallon, you freeze it and you throw it on a roof. You can put a lot of weight on a structure in a very small area pretty quickly.
Right. Then you add wind load and everything. So that's why when you think about code and minimum standards, you have to know where you're operating. The Midwest operates with a slightly different set of codes than California does with the seismic. Then you get down into the Southeast where we get a lot of hurricanes. They have a different set of codes where they need more strapping and things like that. So you have to know where you're working. We want to, at the bare minimum, we've got to hit that level and then work up from there.
Right.
So after we'd have all of our either rafters or trusses built. We'd even have temporary bracing, right? Because we wouldn't have our sheet goods on the roof yet. Those come at a later step. So we'd have some temporary, usually 2x4, 16 footers, 2x6s, sometimes going up at a zigzag, like starting in this corner, working our way up, back down, back up again, just as temporary bracing to keep those dominoes from falling over. And that's where a good constructor is going to be looking at the weather. We want to be safe when we lift those trusses up. We can't have lightning, we can't have heavy wind. It's not safe for anybody on the job site. But we also want to know if we can't get our decking on, and in many cases we can't, the same day we do the lift, we need to get our bracing done, because overnight, if we get into any wind, those trusses or rafters are pretty weak because we've only done the first couple of steps. We just don't want them to start tilting over like dominoes, because then the whole system will fold over. And once they're damaged or cracked, you can't repair them.
It's a horrible feeling when you come back and your structure's in a pile.
Yeah.
I had the auspicious occasion to see that happen, and it happened so quick I was shocked. We were building in the brick and glass market here locally, so the house was about 600K, and this has been many, many years ago, about 7,000 square foot.
Wow.
And it was a very complicated truss system. You know how roofs are today, multiple lines, hips, valleys everywhere, different shapes. It was one of those roofs, and we were up all day getting most everything up, and here the storm starts. So you're starting to see, the black in the sky, the wind starting to pick up. Well, as crews do sometimes, everybody ran for their vehicles,
Right.
and we hadn't finished bracing off the roof. We thought it was just a flash storm. I was young in my career and didn't know any better. The boss said, just go get in your trucks, we'll finish it up when it's done raining. Well, it took 5 minutes after the rain started that roof started to do this. Mm-hmm. And I would say within 30 seconds of this oscillation of movement, it was just this ripple effect, it just over. And then it was just pixie sticks.
Right.
And really, pretty much cleaned everything out. Had to replace probably 50% of the wall framing
Down
was
below.
jacked. Mm-hmm. So really, it was a big enough mistake that insurance, we had to work off of,
Sure.
of
Yeah.
an insurance claim at that point.
And it happens. Sometimes you've done everything right and Mother Nature's still too strong at that particular point when the structure isn't finished. And sometimes it's just people trying to go fast. And in one of my circumstances, the crane operator, we were working out on the west side of Indiana, so very few trees, high wind area. We had done our lift, storm was coming. We had maybe 6 trusses to go. And I was young in my career, and I said, shut it down. We're not going to get these last 6 done. It's going to be unsafe. Because with the trusses, with our gable end, a lot of times we would sheet that gable, meaning we'd put our wall sheathing, the OSB, on the gable while it was on the ground, and then we'd let the crane pick the whole thing up. So I was arguing with the crane operator because he said, hey, this was a long drive. If we just push through, we're going to get this done. So I was young. I thought, okay, he knows what he's doing. He's the crane operator. So we lift up the gable. We have one tag line on the gable, and the gable's probably 40 foot across, 20 foot high in the middle. It's got its chicken runs or ladders on it, all sheeted. I'm the person on the tag line, which is a rope that we hook onto the end to try to control whatever we're lifting up. We get it about 20 feet in the air, and he starts to rotate the grain to lift it in, and the wind gusted and hit that gable like a kite. It shot this way. I held on as long as I could. It yanked me off my feet. I lost my grip, and it swung and almost took everybody off the top plate. We had people dive off the top plate and try to hold on, and almost had somebody killed. And at that point, I realized that I'm the one in charge, and my lack of a spine at that point for standing up of what I knew needed to be done, quickly got strengthened. And we shut down the job and did it at a time that was appropriate. So you got to be careful, because that momentary lapse of, well, maybe it's going to be okay, is usually the time when it's not okay. And I was fortunate enough that we didn't get anybody hurt.
And we'll go through rigging, proper rigging, when it's right to lift, when it isn't. You'll get a lot of that in our steel segments, and then in your OSHA 110 class.
Yep. So after we've got our rafters and our trusses up, it's now time to put on the next component. And a lot of people will think, well, that's going right to roof sheathing. But we've got another step. We need to put in our sub-fascia, or our gutter board. So this piece right here, we just used a 2x4. In the field, we would base our sub-fascia, or gutter board, on our rafter tail or truss tail height. So this piece serves a lot of different functions. So Scott said earlier, this part of our structure is called a soffit. It's also called an overhang, an eave. It's got several terms. This part is our fascia, and it's basically a trim board. But before the trim board or the covering goes on, we need to have a structural member, and it serves multiple functions. We need to put this member on, it's a linear, and that helps tie our truss tails or our rafter tails together and keeps them from spreading this way. The other function of this board is we set it at the proper height, and we'll get out a speed square or a framing square and show you what we mean. It gives a spot for our roof decking to slide down and hit, and gives it just a little bit more blocking and bracing, because of course we're going to attach our roof decking this way, but it gives us a kind of a stopping point here. So this is a very crucial piece that goes on the structure. It's called a sub-fascia, because we would have our fascia piece that would go over the top of the construction material and make it, look more attractive. So Scott, if you can show us, if we didn't drop this piece down, we would actually, the bottom part of our sheet would come in and slide and hit the back of the subfascia. That's a problem when we talk about water concerns and things like that. But if we lower our subfascia down, you can see the bottom of our sheet, represented by the bottom of the framing square, would slide right along and hit right at this 90 degree of our subfascia. That's a good, clean intersection, because the last thing we want is for our roof decking to get a slight curl up. If we curl that up, all that's going to do is slow down rain, or worst case, it slows down ice melt. As the roof heats up, maybe under the winter sun, it starts to melt, and then it reforms as ice because it's not falling off because of the curl, and then it wants to creep back under our shingles. During our shingle segment, we'll talk a little bit more about ice and water shield, ice damming, things like that, but it starts with this piece. So if you look closely, you can see we've got our rafter tail here, a truss tail. We've got another one right over here, and there's an extra block that's been put on. So this is what happens. We want to learn in our lab, but sometimes we learn by making mistakes. So usually we let our students go ahead and frame the roof, and then they immediately go run and they start putting on our subfascia or our gutter board. They lift it too high a lot of times, and we show them the trick with the framing square. But the other thing they do is they stand back and look at their work. And if we have lowered or raised the top of our rafter, that will change how far that rafter sticks out from the wall down here. Or maybe they just cut it wrong. They had the overall length and they cut it a little too short. Well, if it's too short, that's what these shims are. You can see we've put a shim in right here. We've put a shim in right here. We had no shim right here. So these tell us that the rafter tail was pushed in towards the house. But if we need a consistent 12-inch overhang, we have to bring this out. So we were able to achieve that. We did a string line attached here, ran it all the way down the structure, and we can trim off the truss tails or rafter tails that are too long, and then we have to shim out the ones that are too short. Because what we want to do is throwing my tape measure. What we want to do is be able to look right down that gutter board or subfascia and see a nice, clean, straight line, because that's what our owner's going to see, right? They want nice, crisp, clean lines.
Right.
So we have to clean up our work.
Yeah, but when I was taught to frame a roof, what we did is we ran all of these tails long, so we didn't have that problem.
Right.
We'd come back and then we'd snap a chalk line, exact distance of where we needed to be on the back side of our subfascia, and then we would cut those all perfectly in the same spot down through the run of flies.
Right.
So that way, it's just really an extra step, but it gets you that crisp line that everybody wants to see when you're sighting down the eave.
Right. And we started that process, Scott, in our earlier discussions. We started that check the work before you.
Absolutely.
All the way down at the foundation where we would plumb and square and level. And then we did it again with our sill plate, our floor system. We did it when we chalked our lines for our wall as it went in. All we're doing is making those little adjustments as we climb the building. And what you just described is another adjustment as we came up through. It's even more important when we talk about those trusses, because the trusses are all being made off site.
Right.
And again, mistakes happen. It's not the end of the world. It's knowing, what are we going for? What does the overhang say? Am I a little long or am I a little short? And can we make those adjustments?
Right.
It's great when you run them long in a rafter, because then everything is crisp and clean. When we're bringing that pre-built component, we still have fixes, but somebody has to be paying attention.
Right.
So after we get our gutter board in, it's time to go ahead and put on roof decking. And this all, we're beating everybody over the head with it. It's all plans and specs. Do the plans and specs call for a 7/16 OSB oriented strand board? Does it call for 1/2 inch, 5/8, 3/4? It all depends on what the plans and specs say. So we have to read those so we know what material we need. Does it call for ply clips, which is another little component? We talk about a ply clip. There's one here. This is a ply clip that is made for 7/16. It's actually stamped right on the ply clip, so we know that we've got the right size. And what that clip does, it's called an H clip as well, because of the H configuration. It's going to slide over one sheet, and then the next sheet gets to slide down into it. And we can see the example of the ply clips here. So the ply clips are in between each one of our rafters, or if we were using trusses. Why would we need that, Scott, in between?
For deflection between our bearing points or the rafters.
So meaning that sheet at that joint, at that seam, those sheets could have a deflection where they start to separate.
Right.
And we're going to see that in the finished product. We want the roof to be as strong as possible. These steel clips can fit in there, and that provides the rigidity that we're looking for between the two sheets, in between the truss members. Now, we may not need those if our plans and specs called for 12 inches on center or a tighter dimension between our rafters and our trusses. But in this case, with 2 foot, with the roof decking we were using, we needed to use an H clip or a ply clip. But we would do layout again. So we can see our layout here. We were worried about how accurate were these members cut. So this would be another part of our QA/QC. We know the sheet comes 4x8 typically that we need for our roofing. So you can see that our students have run a chalk line, and they marked it at 4 foot up, took a chalk line across the rafters and snapped that line so they could lay in the sheet so that we would have a consistent measurement off of the 4 foot, not necessarily off of the work that was done before them.
So really the rule of thumb is such, and you can see it all through every system and every step of the way, we're setting our materials to snapped lines. That's how we maintain a straight line. Because if we start following other people's work and not going from a point to another point across the structure, all you're going to do is compound their mistakes.
Right.
And everything starts to get, real wavy as you start to go through. And that's the one thing that owners don't want. When they spend money, and they spend good money, they want the quality that they pay for. So it's our responsibility as constructors to monitor that QA/QC, and that's just quality assurance and quality control. And it's our job to maintain the quality control aspect in the field.
Always check that work that was done before you. It's not disrespectful. It's checking the work that was done so you know where did that team stop, where are you picking up the work and you work through. Scott, if you came to a foundation company is done, they've pulled off the job, you show up as the constructor and you're doing a little QA/QC. If you measured that foundation, everything's nice and in plumb, everything's nice and level, but you found it out of square 1/4 of an inch. And let's say that 1/4 of an inch was over the whole 50 or 60 foot length of the building. You'd probably be okay with that 1/4 of an inch.
I'd be happy with 1/4 because in actuality, if we were to square that structure, we would only shift it 1/8 of an inch, right? Half of the error.
So you would take those sill plates and shift them 1/8 of an inch and pick up half of your air. Then if we wanted to be spot on, you could take your floor system and shift it. Now we got to go 1/2 of an eighth. So you're talking about shifting the floor system 1/16 of an inch in 60 feet. Most people can't even see that.
Right.
So that's
right.
what we're talking about, making our adjustments. Now, let me ask you the same question. You come and it's 1/4 of an inch and you go, we can live with that. And you leave. Then they set their sill plates and they don't set their sill plates exactly right. And maybe that 1/4 of an inch grows to 1/2 of an inch. Right. Then the floor system goes on. Then the walls go on. Then we get all the way up to this level. That air can magnify.
Oh my gosh, now we're up here cutting rafters and we're figuring on the width of the building and what the pitch of the structure is, the roof.
Right.
So that's how we're going, and we're going to use a framing square for this. So this is an 812 pitched roof. So this is about as steep as anybody really safely should be walking on without some sort of, let's say a higher level of safety than what
right.
we typically would have to do per ocean. Okay.
So if that air has worked its way up in the building.
Yes, thank you. So we're up at the top, we're cutting rafters. If I'm out of square, all of a sudden, my rafters are short, my rafters are long. And now I don't know what's going on because there's no efficiency with cutting each individual length, taping it, measuring, having to cut the roof in that way.
Right.
It's going to look terrible and it's going to take way too much time. So by not paying attention down on the foundation, really starting with the footing, coming up and adjusting at every step, through every new system, we're going to end up with something that's not going to work. It's going to cost us extra money, and we may run the risk of losing money, and it's never a good day in construction when you're losing money.
Absolutely. And think about the air if we've ordered our truss package. We ordered the truss package at foundation, and it might take 2 or 3 weeks to manufacture
right.
those trusses. They get delivered to the site. We found out that the air kept compounding as it went up, and now we can't use the truss package. That could have been a $10,000, $15,000, $20,000 mistake, and the trusses no longer fit. And with an engineered product, you're not allowed to cut it and modify it without a new design. Right. So not only did you lose time, you could have lost a tremendous sum of money, right. especially when we start looking at the compounding error of the mistake, the $1 to the $10 to the $100 issue.
So the devil's in the detail. It's the small details that we have to be aware of as the process is going on so that we can key on those small details to a degree that breeds success on our projects. Because if you're looking at the little things, you've already ascertained that the big things are going well.
Right, right. And you set that tone in the project as
Absolutely.
The constructor. You set it and you check plumb, level, and square. You check that we've got the right spec'd material on site because, let's face it, sometimes the wrong material is delivered, or it's the right material, it was just delivered to the wrong job site. Somebody sets that tone, and if you've done your job well, the rest of the crews on the site start to live up to your expectations.
Absolutely.
And if you let it slide, they're going to let it slide.
And if you start a dialogue with your subs early on before work begins and you come up with a plan of action, you're able to control those small details at a higher level of efficiency because we've already set expectations for what has to happen while we're putting the roof on. So if we've set these expectations with every subcontractor, excuse me, or with every person on our crew, and they know what they're to do, then it's easy for you as the manager to come and make sure it's happening. But if you're having to teach or you're having to direct in real time when things are going wrong, it's not a good place to be in because it's never going to make you money.
So now in our roofing sequence, our rafters or our trusses are in place. We've cleaned up our rafter tails or truss tails. We've put on our subfascia. We've struck our lines to square up our sheets, and we've started to run all of our roof decking or roof sheathing. We've got our ply clips in. We do want to pay attention because if we've done our layout right, we do have the indicators on the sheet, the green lines that show us where to put our fasteners. So if we're laid out our sheet goods right, we can hit our 2-foot centers, which is what our layout is for our rafters here, and we know exactly where to nail because as we cover up the structure, we can't see, our installers can't see. Plus they're usually working really fast with air-driven guns or gas-driven guns and shooting very rapidly. We need them to get that fastener, the mechanical fastener, into the structure. So that's what our lines on our sheet goods will help us do. You can see here in the example, we've staggered our joints just like we did in our floor decking where we don't want those seams to line up. Here we've got a 4x8 sheet and you can see the 4x8 sheet above this one is broken on the stagger. So the middle of this sheet hits the end of the sheet below it. And that way we stagger our joints and we strengthen up our structure as good as we can. This member here is just the toe kick. So this is not a permanent member. We'd attach this based on whether it's a safety protocol or just an ease of working on the roof. This is a place where the installer can be sitting on the roof and put their feet down against the toe kick and have a little bit of bracing while they're working on the roof. It also helps if a tool slides down the roof, it could catch the tool before it hit the ground. You'll have your OSHA 110. Your OSHA 10-hour card, you'll get the training, you'll understand what we mean about fall protection. But here, since we're less than 6 feet off the ground, we just had a toe kick installed. So this is not a permanent member. It will come off when we go on to our roof finish sequence.
So where would we find our nailing patterns for our sheeting?
So that, again, is going to come down to plans and specs and building code for your part of the country. In one part of the country, if there's no snow load, the spacing, the diameter of the mechanical fastener, and the length of the mechanical fastener may be one spec. We get into a heavier wind load, they may move those fasteners closer together. They may increase the length of the fastener or the type of the fastener to try to hold the decking down to the roof structure and then hold the roof structure to the top of the wall.
Are we using adhesive up here under the decking
No.
to the rafter like we do to a floor joist to the subfloor?
That's a great question. When we get up to the roof level, there are no adhesives. Okay. Really, we don't want anybody walking on the roof. We use that adhesive there to try to help out with those voids between the members and squeaking. We really don't want anybody walking on this roof when it's done. Occasionally, it has to be done for a maintenance reason, right, but we don't want it there.
Is there also some where it really needs to be able to move a little bit?
Absolutely, because remember, this space here in our attic, if I have a lid on the room here, this is where my insulation is going to go, unless it would be a hot roof, which is a whole different setup. But if it's a traditional construction, this airspace right here is unconditioned space. That means if it's 100 degrees outside, it might be 140 degrees here because we're building up heat, and we'll talk about how to vent that heat here shortly. Conversely, if it's 20 degrees outside, It might be 20 degrees in the attic. It could even be colder because we're not picking up the radiant heat that you'd get on your skin. So it's 20 degrees outside, but we get some sun on our clothing. You feel a little bit warmer. In the attic, you can't pick up that radiant heat, so it may even feel colder than 20 degrees in the attic. So at that point, Scott, to what you were describing, we've got big movements or swings of air temperature in that attic. This is all going to move a little bit.
Right, right.
So we have to pay attention to what the plans and specs are, what does the manufacturer tell us, and what is the best component to use. They make all kinds of roof sheathing. They make roof sheathing that has a radiant foil on the underneath side to try to radiate temperature loss back into the house. There's some that have a protective coating on the outside, and all you have to do is tape the joints, and that automatically counts as your roof felt. There's dozens of systems. No matter what system you use, is it the right product at the right job site? And have you read the installation instructions and fully understand how to install that product?
Guys, another key point, always pay attention to your manufacturer's instruction. If you don't follow it, it may very well, and I would hazard to say that in most instances, it would void your warranty. And that's something that we're banking on our materials warranty.
Right.
Because if the company doesn't make good on the warranty, who's going to end up paying for it in the long run? It's going to be the contractor that's responsible for the job.
And one of the easiest things to do is read the instructions and install it the way it was intended. But that takes time. And that's where we'll see constructors say, I've installed something just like this. It's fine, just put it on the way we did the last job. Well, if it's not the exact same material, and maybe it has an extra facing layer, maybe it's a different composite structure within the manufactured product, maybe it's not an OSB, maybe it's another type of material. If you use the wrong fastener, the manufacturer is going to say no warranty because you didn't follow our instructions.
Right. And it doesn't mean that everything that's happening to where that material's working is happening at the location where you're going to do it. A wrong installation again.
Right. Yeah, and this is a key, obviously everything we do in the structure is vitally important. So you can't get to the top of the building and say it's good enough because it affects everything down below it.
And we as constructors can't say it was good enough last time.
No. The product changes, the weather changes, our capabilities of our field crew change over time. I guess that's part of the exciting part of being in construction, is it never stays the same. Our components, our names for some of those components have a tradition of hanging on, but this product wasn't around a few decades ago.
That's right.
Trusses weren't around a few decades ago. Right. Engineered floor systems weren't around. So things do change. They change slow in construction for the most part, or they traditionally have, but they do change. And if you get to the point where you say, I know what I'm doing, I don't need to read about that product, I don't need to understand it, that's when you're going to have a major mistake.
Absolutely.